Hey everyone, it's David with Streaming Relativity, home of the AstroDNA Observatory. I did it! I finally got an image of the hidden galaxy using my Astro Tech 115 EDT refractor, and it was hiding in the constellation Camelopardalis. And I will tell you, this is a difficult a target to grab, and you have to be very patient. You're going to have to capture a lot of data across your broadband channels. I even recommend doing a little bit of hydrogen alpha for this one. And you certainly have to be prepared for some perhaps tricky processing in Pixinsight to be able to draw out this beautiful image. And in this video, we're going to take a tour of IC342, of the hidden galaxy, and we'll talk about some of its features, some of its cool features, and of course, I'll talk about how you can capture this galaxy yourself. And at the end, I'll summarize some of the Pixinsight workflow that I use to reveal this image. And if you like this kind of content, please go ahead, subscribe. I'm putting up videos usually at least once a week, and I think we've got a really cool community that's forming here, and I would love to have you be a part of it. And with that, let's go ahead and take a tour of the hidden galaxy. Okay, so back in July 2023, the European Space Agency launched Euclid, which is a wide-angled telescope with a 600 megapixel camera on it. And one of the very first targets that it chose was the IC342, or the hidden galaxy. Now, that mission cost about $1.5 billion all in, and of course the image is beautiful, but I think we did okay with our modest 115 millimeter refractor as well. So IC342, the hidden galaxy, it's a spiral galaxy, and it's found in the constellation Camelopardalis, and it was discovered early in 1892 by William Frederick Denning, and it's relatively close to the Milky Way. It lies at about a distance of, let's call it 10 million light years from Earth. To give a little perspective, Andromeda is about 2.5 million light years away. So this is pretty close, this galaxy, and in fact, at one point, Edwin Hubble thought it was part of our local group. Now, we know it's not. It's actually part of the Mafi group, which itself is made up of two subgroups, and IC342 is the largest galaxy in one of those subgroups. And if galaxy groupings and clusters and superclusters are terms that you're not familiar with, go ahead and check out a recent video I did on the structure of the universe using my AT115 EDT. It covers all those terms, and I'll leave a link for it in the description below. Now, it was kind of tough for me to find an image that illustrates the location of this Mafi group relative to our local group, but I did find this one, which was posted in Italian, and I'm glad, because in addition to showing IC342, it shows the M81 group as well, and they're about equidistant from the Milky Way at around 11 million light years. And also, when we look at the Bode's galaxy M81 itself, these two galaxies are about the same size. M81 is about 90,000 light years in diameter, where IC342, the hidden galaxy, is about 75,000 light years. So it's a little bit smaller, but not much. This is also reflected in their apparent sizes. Now, apparent sizes are measured in minutes of arc, and M81 measures around 27 by 14, and but the apparent size of IC342, the hidden galaxy, is about 20, let's call it 20 arc minutes, and that's about 2/3 the size of the full moon. Again, that's a pretty big object in astronomical terms, and so why can't we see it easily? You would think that it'd be really apparent in the sky. In fact, you know, if it weren't for a number of factors, which I'll discuss now, this would be one of the brightest galaxies in the sky, and we certainly would be able to see it with our naked eye. Okay, the first issue that we have with IC342 is called galactic plane obstruction. And here we are looking at, let's pretend, an edge-on view of the Milky Way galaxy, our galaxy. You can see there's a central bulge, and then you can see that there is this galactic plane that extends, in our case, about 100,000 light years in diameter. Now, IC342 is located very close to this plane, and this means that the line of sight towards IC342 intersects with all of the dense regions of interstellar dust and gas within our own galaxy. And that dust obscures much of the light that's emitted by IC342, the photons, and it makes it very difficult for us to observe an image because there's so much obstruction. The other issue that we have is that IC342 has a very low surface brightness, and when you compare it to other nearby galaxies like Andromeda or Triangulum M33, IC342 has a relatively low brightness, and we can see that here even in one subframe of the luminance filter, with the luminance filter that I took that evening. It's a very faint object, and this means that the light that's emitted by that galaxy is spread out over a relatively large area, and it's challenging, and it's fainter and challenging to detect by our sensors. So you have to really get your exposures right here, and a lot of frames to stack. Another thing that makes it difficult, and this is less so nowadays with our go-to mounts, but IC342 is kind of situated in a region of the sky where there aren't a lot of good reference stars. Now, there are some deep sky objects that serve as good reference for it, but it's difficult for astronomers who are, let's say, going out to try and observe it to locate it. So you can take a look here on the sky chart just to get a sense for where exactly IC342 is located, and you'll see the issue. Finally, light pollution. Because this is a dim object, because we have galactic plane obstruction, timing for viewing this, or for imaging this object is critical. Now, I happen to have done this with a full moon. I did it because the moon was a good distance away from the object, and I didn't want to lose the evening, and I decided to give it a shot, and it turns out that I was able to get enough data to create a nice image. But light pollution is the enemy of this target, particularly if you live nearby cities or towns, or the moon is out. You're going to need to plan this object out real carefully. But let's take a look at my session details and see how I was able to get this image. Okay, I keep a log of all the imaging that I do, all the objects, mostly so I can always refer to it in the future and replicate it if I need to. And so obviously, the target here was IC432. I captured the data starting on the evening of March 21st. And continued through, obviously, into the morning. I started around, looks like around a little after 8 o'clock, and I finished around 3 in the morning. So it's a 5-hour period. The sequence ran over 5 hours. I collected a little over 4 hours worth of data, and that, of course, was from my observatory here in Warwick, New York. And for those who are interested, the right ascension is 3 hours, 49 minutes, 7.36 seconds, and the declination is 68 degrees, 10 minutes, 28.7 seconds. That's actually pretty high in the sky. In fact, it's one of the objects that we can call a circumpolar object, meaning that it's near Polaris, relatively close to Polaris, so it's always visible in the sky, and that means that you can get a lot of data on it, and you need all the time that's possible. Yes, I did shoot with a full moon on March 21st. It wasn't quite full, but it was certainly illuminated 88%, and that is a factor, but again, it was distant from the object, so I went ahead with it anyway. My clear sky charts were great. I mean, obviously, seeing was a little off because of the moon, but really nice, clear, no clouds, and I really was able to gather a lot of data. The equipment I used the Astro Tech 115 EDT. This is what I consider a really a great budget refractor in a mid-focal length range. It's after the reducer. There's a 0.8 reducer on it. It's around 644 millimeters of focal length, and I pair that up against my ASI2600MM Pro camera. It's a monochrome camera, so I capture, obviously, I capture channel data, and that's on my CEM 120 mount. and I'm using ZWO filters. Are they the best filters? No, they're not, but they're not terrible either. And in fact, I do like them. So in terms of the channels and the data, the amount of data, total integration, I shot RGB and luminance. That was the primary data that I captured, although I did also capture hydrogen alpha, and I'll talk a little bit about that later. So I did 32-minute exposures at a gain of 0, offset of 50 for each of the broadband RGBs, and then I had an emphasis on luminance. And you can tell from the stacks here, the more data, the better. The more quality data you can get, the better. You get better definition in the luminance channel here than obviously you do in the blue, green, or the red. Although red was a fairly strong signal, I'd say red, green, and then blue were the strongest signals in order of strength. At any rate, with that, in total, this totals up to roughly 3.5 hours of data. Then I got another hour of hydrogen, so 4.5 hours of data to get our image. Why don't we take a closer look at the image and let's tour this galaxy. So, despite being a fairly challenging galaxy to image, IC342 makes an awesome target. It makes for an awesome galactic target. First of all, we have a face-on view of this galaxy, which reveals the entire surface of the galactic disk. And that includes some really cool features that help us in our understanding of galaxies and star formation. Now, the most obvious feature, of course, would be the spiral arms. IC342 is classified as a spiral galaxy, and it's actually a barred spiral galaxy, very similar to our own Milky Way galaxy. And it exhibits these arms that wrap around the central bulge of the galaxy. And even though these arms are obscured by the interstellar dust of our own galaxy, you can clearly see 3 strong arms here, and 1, 2, and then this final third arm. And each of these arms wraps around this central region, which we call the nucleus of the galaxy, or the core of the galaxy. And that is where we have the highest concentration of stars in a galaxy, and often, and most likely, we have a supermassive black hole here. So this is the gravitational center of the galaxy, around which all of the galactic matter is essentially bound to and circling. And if we look more closely here, we see why it gets the barred designation. This is a bar shape at the center of this galaxy, and the spirals develop off of that bar. And so these spiral arms are also where we have a tremendous amount of star formation activity. And this activity is fueled by the presence of all this galactic matter, this molecular gas, that the weight of this gas is collapsing upon itself to form new stars. And that activity actually shows up in the form of hydrogen alpha signal. And and I recommend that you shoot HA on this target, because that HA data can always be overlaid on top of the LRGB image that you've created to really make the hydrogen alpha signal pop, and to really emphasize the activity that's ongoing within this galaxy, the star formation activity within the galaxy. Now, I talked about the molecular dust that we see, and that's what these dark lanes are that help give us the contrast to define the spiral arms. And this is truly a very revealing galactic image, even with its somewhat kind of imperfect shape. It's not there are other galaxies that you can image that show stronger, kind of more symmetric spiral arm formation, but there's a heck of a lot of galaxies out there that are irregular as well. So I just think this is a really intriguing image. The only other thing I'll point out that I think is interesting about this object is that there are these 6 stars that are not part of IC342. Obviously, they're part of our galaxy, but they serve as a really good marker when you are imaging this. You can use this to help orient and frame your shot. I chose to crop and center the photo to resemble what the Euclid Space Telescope imaged, and it helps us to compare the two. Not a bad capture for 4.5 hours of data. Okay, let's talk quickly about the processing workflow for IC342. And now this is a galaxy. It's a different type of workflow than perhaps I've shown in other videos when I'm working with narrowband data. However, I do my stacking with serial, and in this case I actually had to redo my flats. I wasn't happy with the initial outcome. So at any rate, you do your pre-processing, meaning get your stacks, bring your stacks into Pixinsight, do your star align, and crop the image to your taste. Now, I rotated my image and I did a significant crop. Keep in mind that this is 644 millimeter focal length, and that's a wide field of view relative to the size of this image. Again, apparently about 2/3 the size of the moon. So you can imagine I did a significant crop. I tried to minimize loss of data, but I did do a crop on the image and oriented it similar to the Euclid image for purposes of illustrating and telling a story in this video. Now, I use automatic background extractor simply to get a look at what the gradient is. And so I just get the background model. I'm using the gradient correction tool, the latest release with Pixinsight. I think is 1.8.2. There's a new gradient correction tool which seems to do a very good job, particularly with images like galaxies. So I used the gradient correction to neutralize my background. Now here's where we start to get a little bit different. We're still in the linear space. In the linear space, I do something called the linear fit, which is to balance the signals of the R, G, and B channels. And I choose the signal, I chose red as the signal to do the balancing against. And with that, I have linearly fit color channels. You do an RGB channel combination process where you specify R, G, and B, and it will composite an RGB image. Again, in the linear space, you can do an auto stretch on that to take a look at what you've got. You're probably going to have some issues with your colors, not dramatic, but you know, galaxies never produce really beautiful colors without a little bit of manipulation, curves manipulations, etc. But also the stars. You want the stars to try and kind of resemble what you would expect them to be in an RGB image. So you can run SPCC. It's a process that you run against your image, and it will kind of color coordinate your image. You do need to plate solve in advance of running SPCC. Make sure you have Gaia star database installed, and so I did run that process. With that, I then had a linear RGB image, and I had a linear luminance channel, which for both of those linear images, I ran a noise and blur reduction against them. I use RC Astro's tools for this. They're relatively inexpensive and very powerful. And they did a nice job of getting rid of some of the background noise, which you're going to have if you don't have a large number of sub-exposures. And the blur reduction helps to kind of refine some of the detail in the spiral arms, but more importantly, it actually reduces some of the halo effects that you have in your stars with long broadband exposures. With those clean images, I then stretch the luminance and I stretch the RGB files. And so we now have a nonlinear representation of those files. And you can use the LRGB combination tool and simply specify your luminance frame, and then you drop that process onto your RGB nonlinear frame, and it will take the luminance channel and use that to boost the details of your image. I then export that file and I take it into GIMP for some final processing. And generally speaking, within GIMP, all I'm going to do is adjust the curves a little bit so that the background is a little darker and the galaxy features pop a little bit better. But I'm very light-handed when it comes to any kind of processing. And voila, there you have it. You're able to get a fairly decent, not perfect, but a fairly decent image of IC342 with just 4 hours or so worth of data. Okay, why don't we call that a wrap on this video? I hope you enjoyed it. The IC342 is a remarkable target. It takes a little bit of patience, and it deserves a lot more integration time than perhaps I've given it. But I am very satisfied with the image. It told the story, did exactly what I wanted it to do. I have several other images that I've captured with the AT115 EDT that I have not shared yet. A number of nebula photos, and I intend to continue to use the AT115 EDT through the solar eclipse. So if you're interested in this type of stuff, these types of videos, and you're into all things astronomy and astrophotography, go ahead and subscribe. It's the best way to get notified when I publish, and I seem to be publishing at least once a week. And with that, I will see everybody on the next video.